All right, good morning, ladies and gentlemen. Why don't we start on time today, since we do have a lot of things to cover. I'm both happy and sad that I guess today is the last day I get to talk to you before the exam. We'll summarize what we have learned so far this semester, hopefully with the aid of some of my favorite physics experiments and demonstrations. I guess before we start, again, let me remind you that as the semester is winding down, today is the last class. Next week is a triple R week. We'll have a review session with the couple of GSIs running the review session, who will perhaps tell you about some of the more subtle topics. They will review multiple choice questions and maybe give you examples of how to write short answer questions on the exam. The exam will be on Wednesday, about almost 2 weeks from yesterday. Wednesday the 14th, it must be May 14th, here in Pimentel, and the standard rules apply that applied to the midterms. There will be 40 multiple choice questions, 6 short answer questions for 3 hours. It's hopefully reviews and the entire semester, and hopefully you'll be able to demonstrate what you have learned over the entire semester. You'll be allowed 3 pages of notes, double-sided, just like in the first and second midterm, the same rules. Except instead of 1 cheat sheet, you'll be allowed 3. Otherwise, closed book and everything else. No phones, etc. So, if you don't have any logistical concerns, I'm happy to answer physics questions, so I would be happy to answer physics questions as we go along. Please let me know, don't be shy. Actually, there's one more logistical thing before we start. Oh, by the way, I guess you guys realize today is May 1st, otherwise known as May Day in the rest of the world. The United States doesn't recognize it as a holiday because it has communist connotations, well, socialist or labor connotations, and that is somehow not appropriate. Here, the rest of Europe is on holiday today. The rest of Europe. Europe, that, those little countries across the ocean. On holiday, this actually is a picture, this is a Russian, obviously, from 1920s. If you actually look in history books, apparently May Day started as a celebration of the spring somewhere in, I guess, England. But then in the 19th century became a point at which, first the focal point of organizing labor unions, and then the celebration of some of the, I guess, advances in the labor laws in Europe. But for us, this is a celebration of the end of the semester. This is hopefully a celebration of what you have gained, both in knowledge and skills and understanding throughout the semester. So you will demonstrate that set of skills, the knowledge, and the understanding 2 weeks from yesterday at the exam. Before we do that, you know the spiel that I would like you to provide feedback to me. And of course, the department would also like, the physics department and the College of Letters and Sciences would like you to provide the feedback on how effective the class was. So I'll be distributing these yellow evaluation forms. Please fill them out as we go along. I will not look. I'll probably be busy getting hammered. So I'll pass them along. Please pass these forms around. Please fill them out before the end of the class. I'll leave let me send some more this way, if you will. A few more here, and I'll send some that way. I'll come around. There you go. please pass them around, and actually maybe I'll send a few more here. And a few more there, and maybe a few more that way. Maybe more that way, right? And just send them across, and I'll start the same process on that side. While I'm running around, if I can have a volunteer, somebody please raise your hand to collect this at the end of the class. That would be great. So I'll leave an envelope for it. You'll have to find a corner. How about here? So please drop them off as you come down. Can I have somebody to volunteer to put them in an envelope and deliver them to the Department of Physics? Anybody else needs them? Oh, thank you. I'll leave a few more here. Okay. So would somebody please pick them up at the end? Or should I point at somebody? Thank you. All right, so at the end of the class, please come down, put the evaluation forms in the envelope, and what's your name? Melissa. Thank you, Melissa. And Melissa will deliver them to 366 LeConte. That's not very far out of the UA, hopefully. So in the meantime, again, today is all about celebrating the end of the semester, summarizing what we learned in this course, which was the physics of future presidents. Of course, our goal for this course initially, and it still remains, is to educate you in the topics that are relevant for the modern society, the topics that involve fundamental science, technology, and physics as the foundation of that modern technology. This hopefully was a useful course. Hopefully you have gained some understanding of how everything that we look at and everything that we experience in everyday life is based on fundamental physics laws and how those laws apply to the modern society. The book was written by Rich Moller, who hopefully you had the chance to see in flash here about a month ago when he guest lectured about the global warming. Of course, Rich, I know that might be my opinion, yours might differ, but Rich, Professor Moller, clearly looks like a prototypical physicist, right? I mean, he looks almost like this, or like this. So, well, this is a stereotypical scientist. This is a more prototypical scientist. He's highly accomplished, distinguished, even has white hair. Of course, not all physicists look that way. Well, you see an exception here in front of you. I would wish that I would look, at least something like this. Something like this. Of course, maybe my dream is to look like this, perhaps. This is a very famous Russian character, right? Ivan Drago. One of my favorite movies of all time, in fact. It's a comedy, if you are into those types of things. Of course, one is born with what one is born with, right? I don't look like this. Maybe I would wish I could look like that. And in fact, I try. This is another stereotypical scientist, of course, not a physicist, but we're not going to hold it against them. This may be my desired alter ego, as God is my witness, I try, I practice, and sometimes practice pays, and sometimes it doesn't. Sometimes it does. So, I strive for the best, perhaps. Of course, perhaps my real alter ego is somebody like that. I don't know actually how many of you know who that is. Also some Russian character, right? Name is Boris. Of course, our goal here for this semester was, again, educate you as the future members of the society, future world leaders, future decision makers on issues that ultimately will affect policy, on issues that ultimately, hopefully, will affect society. You do need to understand some of the fundamental science, so at least the foundations of the fundamental science to make sometimes difficult decisions. The class is called Physics of Future Presidents with the intention that some of you, many of you, will eventually become policymakers, of course. We didn't tell you that you are going to be educated in, or you'll have a degree from the University of California, Berkeley. Some of the more liberal schools in the US, perhaps, or at least the school with the long history of liberal movements. It's for you to judge how likely it is for somebody graduated from Berkeley to become a US president. I have my opinions, but of course, if that line of work doesn't work for you, you can still work in the positions of power. Or if the US presidency doesn't work for you, you can strive for something else. This guy actually does understand some science. So, being a president is a tough job. Requires mental toughness, sometimes requires apparently physical toughness, or some mature images. It does require you to also trust people. It does require you to have advisors in which you can rely on, but also it does require you to have some knowledge so that you can exercise your own judgment. And that judgment involves both understanding of the world and understanding, of the people around you, countries, some perhaps amount of trust. Let me demonstrate to you that trust is important in life. I'll invite Roberto. There you go. So here's a little demonstration that demonstrates both my trust in people, in particular Roberto, who's helping us out this week with lecture demonstrations, and I trust he's skilled, and also trust in physics. I did this with a student before, and it worked well. This is the bed of nails. This is something that demonstrates my physical toughness. Monks in 16th century could sleep on the devices like this. They're actually rather comfortable. This bed of nails has thousands of That's not quite uniform, actually. Maybe this would be safer, flat. It's about 1,000 nails here, hammered with about half-inch intervals. They will spread my weight over the larger area, and in fact, pressure applied by each of the nails would be correspondingly smaller. I can sit on this bed of nails as my weight, or rather the force applied by gravity, is spread over a larger area, pressure decreases, and so this particular contraption looks rather comfortable, at least not painful. So one trust in the physics laws is the fact the law that relates forces and pressure, the larger the area, the lower the pressure is, and this is a particular demonstration. Now, another example of the physics laws that I need to trust in is the law of inertia. What Roberto will do is try to break a cinder block here over my stomach with a sledgehammer, and my trust in his abilities to not to miss, and my trust in the physics laws will be on display. Now, hopefully you have phones ready for 911 calls just in case. Right. Drum roll. Thank you. Vital organs hopefully intact. This little demo, as we'll discuss later, actually demonstrates the law of inertia. The reason the cinder block breaks on impact rather than accelerates applying force on my stomach is due to inertia of that heavy cinder block. But of course, tricks like this that perhaps belong to a parlor or a circus do require a certain amount of trust, right? A certain amount of trust in physics laws and a certain amount of trust in your colleagues who will not hit you in the places that will hurt. I guess that's lesson number one. Trust is good as long as you understand what's behind it. Now, over the semester, we covered many topics. The first topic we covered was the concept of energy and power, the fact that energy comes in many different forms. The most direct observation of energy is the fact that energy is required to sustain motion, and any moving object contains something known as kinetic energy. Kinetic energy describes the amount of energy contained in a moving body. And this it's example. This bowling ball, relatively heavy bowling ball, requires me to produce mechanical work in order to make this bowling ball move. Once I do that, this bowling ball can oscillate, transforming some amount of kinetic energy into potential and vice versa. And this process can go on for a long periods of time. In fact, if this bowling ball was completely perfect and that suspension over the ceiling there didn't dissipate some of the energy and convert it into heat of the motion of the molecules in the ceiling and also in the area around it, this bowling ball would be oscillating here forever. One of the concepts that we talked about is that the energy is a conserved quantity. It doesn't come from anywhere. It doesn't disappear completely, but it can be transformed from one type to another. And this bowling ball is a demonstration of a transformation of motion, kinetic energy that's related to the speed of the moving object, to potential energy that's related to the elevation of this bowling ball, and vice versa. This is an example of a continuous, repeated transformation of energy, but the total amount of energy contained both in the motion and in the elevation, and the heat of this room, if we take that into account, remains constant. There are many types of energy, so several types of energies we've discussed. Kinetic energy, again, describes motion. Potential energy describes the ability to produce motion at some point. Discuss the potential to produce motion by generating forces. Potential energy also has to do with the energy storage. In other words, you can store energy either by elevating objects by going against some forces. You can store electrical energy in devices known as capacitors, such as like this. And then at some point later, this stored energy can be transformed into other forms, for example, into motion. Here's an example of such an experiment where you can store large amount of energy in some storage device. In this example, it's called a capacitor that can be charged to high voltage. Voltage is again a measure of electric energy stored in a large number of electrons. And that energy can then be released at some point and transformed into other forms. In this particular example, if I charge the capacitor to large voltage, I can later release the energy by discharging this capacitor, in this particular case, by shorting the two electrodes. Thank you. And this is an example of this discharge is a conversion of the electrical energy that's stored in the electrons that are sitting on the electrodes of this capacitor into other form of energy, for example, in the form of a spark, so light energy plus sound, kinetic energy of motion of molecules that propagate through this room, producing a sharp shock wave. And of course, there's also the more fundamental energy source that we discussed later in the semester, the fact that every massive object like this contains vast amounts of energy, independently of whether these objects move or they're sitting somewhere at rest. That amount of energy is known as mass, or mass energy, expressed by Einstein in the formula that conveniently fits on T-shirts, E equals mc squared. It can be viewed in this form, or it can be viewed in this form. I think this particular formula on the left here, square root of E over m, is a C. So the fact that every object, however quickly it moves, independently of how quickly it moves, contains large amounts of energy that can be released under certain conditions. For example, matter and antimatter can annihilate, producing large amounts of energy in the form of gamma ray bursts and flashes of light. The other way to look at this equation is that in order to produce mass, you need to spend energy of some kind. All this leads to practical applications. We discussed early in the semester the issues of the energy economy, the issues that have to do with various forms of energy that's available to humans, such as fossil fuels or nuclear energy, or perhaps solar energy. We have a demonstration here again of a way to convert some types of energy into another. So a solar cell is an example of a conversion of energy of one kind, for example, energy in the motion of the light, energy carried by photons, particles of light. That energy, kinetic energy of that motion, can be converted into electrical energy, and then in turn, electrical energy can be converted into the mechanical energy in some device that's powered by this electricity. So again, energy can be converted from one source to another, and then we discussed various issues that have to do with the efficiency, cost, and also abundance of various energy sources here on Earth, from solar, wind, hydro, and other types of renewable energy, to some energy sources that are not renewable, that are ultimately will be exhausted here on Earth, such as fossil fuels and perhaps nuclear. So later in the semester, once we understand that energy is the most fundamental physical concept, energy is what allows us to power devices, we discussed the fact that energy is transformed from one type to another, from kinetic to potential and vice versa, but ultimately, all sources of energy, all energy that we spend on devices ultimately get dissipated and transformed into the source of energy, into the type of energy which makes it difficult to collect back, and that energy is known as heat. Heat is the energy contained in the random motion of atoms and molecules. And we discussed the fact that this random motion is something that's very difficult to convert back into a orderly, more useful type, like, kinetic energy of a single object or of the, potential energy. Heat is an example of kinetic energy of moving objects, and we measure, so it's one type of the energy which can other sources of energy be transformed into. we discussed the fact that temperature is one measure of this random motion. Temperature in some fundamental physics units is a measure, exactly proportional, is a measure of kinetic energy of single molecule in a gas or solid or liquid. It's a measure of that random motion. And we discussed the fact that some of this randomness can, in fact, be harnessed. In particular, one of the fundamental properties of materials is that materials expand or contract when the temperature of those materials changes. And the reason to understand this is, well, the reason that most materials, in fact, expand when they're heated is because the molecules require more space or require more average spacing between them as their motion increases, as the kinetic energy of their motion increases. And so the fact that most objects expand when they're heated can be used technologically, in particular gases, which is the substance that may be 1,000 times less dense than solids and liquids. Gases are a loose collection of molecules that don't interact very strongly with each other. Gases expand, in fact, dramatically when they're heated. And that fact can be used to produce motion. And a typical example is here. We did this experiment at some point. I have liquid nitrogen here in this thermos that is much denser by about 1,000 times than nitrogen in the gaseous forms that surrounds us, that is a large fraction of air. So when this liquid nitrogen boils and evaporates, the density increases dramatically, and that fact can be used to apply forces on objects and therefore produce motion, like this. So the expansion is a very powerful force. Expansion of the gases can be, where did this cork land? Oh. Expansion of the gases can be used to produce mechanical motion. And that fact, of course, is used very often in heat engines. You know, this particular example is a one-off type conversion of heat into kinetic energy. And, you know, I can repeat it multiple times if I, shoot the cork, go fish it out, pick it up, put it back into the cannon, and do this all over again. Of course, this isn't a very efficient process. A more efficient way to convert heat energy into kinetic, into the energy of motion, is to design a device like this, which operates on a closed cycle, which does this type of repetition over and over again automatically. So effectively, expansion of the gas, producing motion, collecting of the projectile, putting it back into the chamber, redoing the process again. This can be done in a closed cycle in devices known as heat engines. And here's an example of this. This is an example of a so-called Stirling engine that is very similar to the internal combustion engines in most of your cars. The only difference is that in this particular engine, the heat source is outside of the chamber where the gas is expanding and contracting repeatedly. And in your internal combustion engine in your car, the heat source is typically inside. That's a minor difference, but it's an example of a device that converts heat energy produced by burning natural gas into repeated mechanical motion of the wheel. Again, this is an example of harnessing heat energy and using the fact that thermal energy can be used to increase temperature of the gas. Gas expands, creating forces that can be then converted into mechanical motion. This can be done in a cycle, producing a repeatable conversion process, harnessing the heat energy and converting it into mechanical motion. So this is one of the practical applications of heat. Of course, there are perhaps less practical, but nevertheless more impressive applications of heat energy. We know properties of materials change with temperature quite significantly. For example, elasticity of materials can change with temperature quite significantly, and that fact is used by the engineers when they design bridges and buildings. Here is a nice smelly flower, which I can cool by immersing it in liquid nitrogen. I'll let it freeze for a little bit. And you know from personal experience that frozen objects tend to be stiff, tend to be hard. So that's an example of a change in the properties of materials with temperature. And of course, you know, gases contract significantly when they're cooled down to cryogenic temperatures. My lungs are not what they used to be, even though I don't smoke. Oh, good enough. This little balloon, I'll put it also into liquid nitrogen. We'll see what happens to it. We'll see what happens to the flowers as well. The air in the balloon contracts when the balloon is allowed to cool down. I need some more nitrogen. Liquid nitrogen is a great substance. It's one of the most common cryogenic liquids. It boils at the temperature of 77 Kelvin, or 77 degrees above absolute zero, where the absolute zero is defined as the temperature where no molecules move at all, compared to the nominal temperature of our environment of about 300 Kelvin. So it's about 200 degrees lower than the typical room temperature. Here is the flower that I cool down. It becomes very stiff, can be broken easily on impact, and it doesn't smell nice anymore. So properties of materials change with temperatures dramatically. Sizes of the objects decrease when they are cooled down. This is one of the properties that needs to be taken into account when we design buildings that operate over a large range of temperatures. Let's see. What else did I want to demonstrate? Oh, and of course, another demonstration of the large forces that can be applied by moving molecules, even though the molecules themselves are very light and very small and invisible to a naked eye. A large collection of molecules can produce significant effects and significant forces. One example of this is the example where expansion of the molecules can propel this cork across the room. The other example of a very large force that many molecules can produce is the concept of pressure. We live on Earth in the nominal atmosphere filled with nitrogen and oxygen at the pressure of about 1 bar. Well, exactly 1 bar, defined as 1 atmospheric pressure. This pressure is produced by the weight of all of the molecules above us. So the fact that the molecules are sitting near their surface, gravity acts on the molecules, pushes them towards the surface. Those molecules in turn push on us, produce an atmospheric pressure. This atmospheric pressure is a large quantity. Even though each individual molecule is tiny and its weight is insignificantly small, a collection of molecules over the distances of 20 to 30 kilometers above the Earth's surface can produce very large forces. And this is an example of the force that can be produced by such column of air. I have here an oil tank, empty oil can, that contains air inside it. And so the weight of the molecules that are pushing on this oil can from the outside is balanced out by the forces produced by the air inside. And so this oil can is intact when the forces are balanced, but if I remove the air from inside the can, the forces will become unbalanced, and the weight of the air above this on the outside of the oil can be large enough to create significant structural damage, to crush this tank. I'm looking for an on switch. Oh, there you go. On. So evacuating air from inside the tank creates an imbalance of forces, producing large enough forces to crush metal. This is, again, another example of a collective effects, the effect of the large number of molecules exerting their weight on the surfaces. This weight is known as atmospheric pressure, which in human units is measured in the units of about 14.7 pounds per square inch. So every square inch of the Earth's surface is experiencing the pressure, the force, rather, of about 14 pounds, 14.7 pounds per square inch. This is the weight of the column of air above us. And that, again, can produce very significant structural effects. Okay, so this was the concept of heat. We talked about forces in general, the fact that the motion of objects can only be started or stopped by applying external stimuli known as forces. This fact is summarized in 3 Newton's laws. The first law being that any object at rest will remain at rest, and any object in motion will remain in motion forever unless some external stimulus, some external force is applied to it. The second Newton's law describes this concept more quantitatively. It says that the amount of acceleration that an object will experience is proportional to the force. And that proportionality coefficient is the mass. So the Newton's law reads F equals ma. That, incidentally, is the second equation in the back of my T-shirt. F over m is supposed to stand for A. And I guess we'll get through the last symbol in just a little bit. So the concepts of inertia can be, the fact that the objects can be moved by applying external forces, and the amount of motion depends on how inertial rather, the objects are. Mass of any body measures that concept, that amount of inertia. So understanding this can lead to, again, practical applications. For example, restaurant tricks that you can perform if you, again, have complete trust in the applications of laws of physics, in this case, the second law. Sort of works. The fact that in order to move objects, you need to apply forces to them. And in general, the massive objects don't like to move. The inertia is a measure of how difficult it is to produce accelerations. This particular example was jerking the tablecloth from underneath the dishes, produces very little force, applies very little force to this object, and so motion of the tablecloth near the plate is not enough to produce motion. Direct application of the force is required. So, okay, inertial objects don't like moving. I hopefully demonstrated this to you when I was hit with a sledgehammer, or rather the cinder block that's heavy didn't like moving, and in fact it broke before it could move quickly enough to produce damage to my internal organs. This is again a concept of inertia. Heavy objects don't like moving, and require large enough force in order to get them to move. We also discussed the concept of conservation laws, the fact that there are quantities such as energy that are constant of nature, that can be transferred from energy, is the type, is a number that can be, or the quantity that can be transferred from one type to another, but on the whole can remain constant, remain conserved. Another slightly less obvious quantity that's a conserved quantity is the angular momentum, which measures the amount of rotational motion. And so if you make an object, if you take some object like this and make it rotate like that, the rotational motion, this rotational motion can be described by the concept of angular momentum. Angular momentum tells you about the speed, or is the quantity that describes the speed of the rotational motion times the distance from the origin, from the center of this rotation. And one of the conservation laws tells you that unless there are forces, well, rather known as torques, that prevent or either that act on this rotating body, angular momentum in the system of rotating bodies tends to be conserved. Physicists understand this, in fact, from the fundamental principles. We understand this as a symmetry, a certain symmetry of nature. And in the case of rotational motion, the symmetry describes the uniformity of space in all directions. This law of conservation of angular momentum can lead to interesting effects, some of them more intuitive than others. So here I have a device, this very manly pink suitcase, and a device inside the suitcase. I will start. In a second. All right. So I have this nice suitcase. I'm traveling to Italy next week. I can take it with me. How do suitcases usually behave? If you go through airport security and you put the suitcase on the table, what do you think would happen? Well, suppose I want to put the suitcase on the table. It has a mind of its own. I want to put it on the, right? I want to put it on some conveyor belt so that TSA can check the contents, and it doesn't like to lay flat. If you guys want to handle it, want to handle it? It's relatively heavy, but that's not an issue. Try moving it around. It behaves weirdly. This is an interesting device. This is a device, inside the suitcase is a device. Inside the suitcase is a device, rotating flywheel. This is a device known as a gyroscope. In fact, this is a very massive wheel that spins, and the angular momentum, this amount of motion, rotational motion, likes to be conserved in this device. And so if I move it around, if I change orientation of this flywheel, this flywheel will produce torques that counterbalance my application of forces. It's due to the fact that angular momentum in a spinning body tends to be conserved unless I apply external forces. This concept, in fact, is what makes some devices work. For example, I'm going to see now. you know that, well, actually, one of the things that makes bicycles go on a straight line or makes bicycle turn when you lean off to one side is the conservation of angular momentum. What's this device that people ride on that has like platform and the wheels, and I go completely senile and forget. Segway, thank you. Right, Segway has about 3 or 4 gyroscopes, flywheels like this, that are designed to keep the orientation of the Segway in one particular direction, vertical. And then if you lean into it forwards, the Segway produces enough torque to counterbalance this leaning and produces forward motion. If you lean sideways, it turns. Again, this is based on the conservation of angular momentum. It has some of these spinning heavy flywheels inside it. Thank you. This is an example of the practical application of conservation of angular momentum. Okay, so later in the semester we discussed radioactivity, because radioactivity is an example of a quantum process. It's an example of a decay, spontaneous decay of nuclei. Some of these heavy nuclei in the periodic table, such as uranium or perhaps plutonium, or maybe some of the light isotopes such as potassium. Radioactivity surrounds all of us. Some of these heavy elements, uranium and plutonium, were produced in the explosion of supernovae, some number of them, that produces these heavy elements. These heavy elements have typical lifetime of about 1 billion years or more. So uranium and thorium, those are the 2 most commonly common radioactive elements found in the Earth's crust. Those are examples of the unstable nuclei that spontaneously decay, exhibiting one of the laws of physics that we described later in the semester, known as tunneling effect in quantum mechanics, which describes a process that can happen where if it's not disallowed by any laws of nature. The nuclear decay is an example of a nucleus spontaneously breaking the forces that are trying to hold it together, and that's an example of a quantum tunneling effect. Nevertheless, these nuclei that sit in Earth's crust, thorium and uranium, or potassium. Potassium is contained in small quantities in human body or in fruits and vegetables like bananas. Is an example of a radioactive isotope that produces ionizing high-energy radiation known as alpha, beta, gamma particles. We can measure the amount of radiation using Geiger counters, so devices that will trigger an electrical signal when a high-energy gamma, alpha, or beta ray passes through it. So this is a way to measure the amount of radioactivity in the environment or amount of radioactivity in some particular devices. For example, this old radium actually infused watch, in which the radium painted on the hands of the watch is used to produce luminescence, to produce light, so that this watch can glow in the dark and can be viewed in the dark. This obviously isn't good for customers that wear the watches, since the ionizing radiation is called ionizing radiation because it has enough energy to separate electrons from the nuclei in the atoms, which in devices like Geiger counters produce audible signals, but in human tissue can produce biological damage and ultimately cause either acute radiation sickness in large doses or long-term effects such as creation of cancers. So we discussed these issues, also the fact that we are constantly bombarded by radiation, either in the form of spontaneous radiation from uranium and thorium or potassium decays, or in the form of cosmic rays that are produced in the upper atmosphere at the elevation of about 20 to 30 kilometers, when the solar wind, hydrogen nuclei, protons, are ejected from the sun, travel the 8 light minute distance between the Earth and the sun, and collide with the nitrogen and oxygen nuclei in the solar, rather in the Earth's atmosphere, producing unstable, radioactive, short-lived particles called as known as muons. These muons have a very short lifetime of about 2 microseconds. So nominally, if they travel with the speed of light, that will travel a distance of about 600 meters or so. However, they experience the effect known as time dilation that we discussed later in the semester. That's an example of an application of Einstein's theory of special relativity that says that any moving clocks in some frame of reference that's moving with respect to a stationary reference frame slow down. So muons that are unstable, radioactive, high-energy particles are produced in the upper atmosphere and actually can still penetrate through 20 kilometers of air down to the Earth's surface, and they continuously bombard you. The typical rate of those muons is about 1 per minute per an area of about square centimeter, which is incidentally the area of your iris in your eye. So some high-energy particle hits you in the eyeball about once a minute, or if you integrate over your entire body surface, there's a few of those muons penetrating through you every second. Of course, they are relatively benign. They leave a relatively small amount of energy in your body. They just slice through you like a knife through butter and then go on to their happy, merry ways. But they do deposit energy, and that energy can, in principle, cause long-term biological effects, such as creations of cancers. So muons and the nature of radioactivity are examples of radiation that continuously exists in the environment and we experience every day. And of course, understanding how that radiation affects us and how increases in radiation exposure can increase the cause of cancer, can increase the rate of cancers is an important numerical fact that I hope you remember from this class. The fact that it takes a large amount of extra radioactive exposure, such as about 2,500 rems in the standard units, or 25 sieverts, to increase the rate of cancers by about 100%. So an increase in radiation exposure can increase your cancer rates by a known amount. So you can judge, and when you're making policy decisions, you can judge how a particular radiation exposure is relevant. We discussed nuclear energy and nuclear power. The fact that spontaneous chain reactions can be produced by neutrons hitting a uranium or plutonium nucleus, causing those nuclei to split. That splitting produces extra neutrons that can hit other uranium and plutonium nuclei that causes them to split, producing more neutrons, thereby producing a chain avalanche-like reaction. An example of such chain reaction is here. We have armed mousetraps that have little balls that are to represent neutrons, and a single neutron coming from the outside can trigger the mousetraps that will trigger some other mousetraps that will trigger some mousetraps very quickly, releasing all of the energy stored in the springs of the mousetraps in one quick explosion. This is an example of a chain reaction. This is exactly how the nuclear explosions work, by a single neutron stimulating the decay of uranium or plutonium nuclei that can in turn stimulate a decay of other nuclei in a chain reaction. So we discussed how nuclear bombs work. Of course, one can use this process slowly. Instead of having a single neutron produce multiple neutrons when they break up uranium or plutonium nuclei, one can absorb some of the neutrons and actually make a single neutron on average produce exactly one neutron in the uranium nucleus. That would be an example of a controlled reaction where the number of neutrons doesn't decrease over time, an explosive process of release of energy. Explosive release of energy doesn't happen. So when we do this in a controlled way, we can then harness the nuclear energy released in the nuclear reaction in the form of heat, and then convert it to electrical and mechanical energy. So this is how the nuclear power works, is by harnessing the energy from the released in the breakup of the uranium or plutonium fuel in the form of useful, peaceful, hopefully energy like electricity. And of course, we also discussed the issues that society faces when we deal with nuclear power and nuclear energy and nuclear weapons. And those issues involve both the proliferation or non-proliferation of nuclear weapons and spread of nuclear weapon technology to potentially rogue countries like Iran, and the ways world powers can slow this process down or stop it completely, both by diplomatic and other means. And also we discussed what is required for a rogue country like Iran to produce a nuclear weapon, and for example, what's required in this particular case is enrichment of natural uranium to a weapons-grade uranium where the concentration of one particular isotope of uranium-235, that's the isotope that causes nuclear fission, so concentrations of about 80 to 90% are required, which is what some world powers believe Iran is currently trying to attempt. We discussed electricity and magnetism, so we discussed the fact that electricity, electric and magnetic fields are example of forces that can act over distance. And one standard example of this technology, the fact that energy can be carried over distance by electric and magnetic fields. One example of this is electromagnetic radiation that powers devices like your cell phones and Wi-Fi and various other forms of wireless communication. The electric and magnetic fields are produced by electric charges that are either stationary or can move around. We discussed how electricity is produced in the power plants like this, either nuclear or perhaps coal or gas-powered power plants. We discussed the fact that it's most convenient to produce power in electrical power in alternating currents. It's most convenient to produce electrical power where the electrical currents oscillate up and down, change in value and direction. This has to do with both how electrical power is produced by a rotating turbine that tends to produce the power, electrical power that oscillates, otherwise known as AC, but also the fact that AC electricity is very easy to change. It's easy to employ devices like transformers to change electrical voltage and electrical current, to either increase or decrease it, to either step electrical voltage up or step electrical voltage down. An example of such device is here. This is the Tesla coil, which is a very powerful transformer. It's somewhat humid today. So this transformer can increase the voltage, can step up the voltage from the normal power outlet of about 110 volts to a significantly larger voltages, large enough to ionize air and to produce electrical sparks. this, otherwise known as lightning bolts. And we discussed issues of electrical safety, the fact that very high currents are dangerous for human body, but high voltage is not necessarily dangerous, depending on whether the device can produce high electrical currents. So this large voltage can produce lightning sparks. Can light lamps. But if the electrical current flowing through a body is small enough, this can be the effect of the electricity on the human body is small. So this is a Tesla coil. Tesla coil is the device that steps the voltage up to the values of about 1,000 or 10,000 volts. Producing electrical sparks. Of course, if you have a device that can produce very large currents, such as your electrical car, your car battery, the large currents can cause dangerous biological effects, can burn tissue, or if the electrical current is running at alternating currents, can produce fibrillation and other effects. Now, motion of electrical charges produces magnetic fields. These magnetic fields can be induced in any metals. An example of this is this device that demonstrates magnetic induction. Whoa. So alternating electrical current in a magnet can induce or produces alternating magnetic fields that can induce alternating electrical currents in any metal. Those electrical currents in turn produce magnetic fields that are large enough to levitate massive objects like this. So this is an example of magnetic induction where alternating currents produce alternating electrical currents. And of course, the other effect that is noticeable when the electrical currents flow through such devices is that electrical currents also dissipate energy in the form of heat. So if you don't trust me, you can touch this ball. Be careful. Notice that it's relatively hot. So this is an example of how magnetic induction stoves work in some of your modern kitchens. In the induction stove, the alternating electrical current produces eddy currents in a metal skillets or pans, heating them up. This effect, the magnetic induction, can be also used to propel projectiles, which is how rail guns work. Here's an example of such a device. I can send an electrical current through a large transformer that will induce an eddy current in the closed loop ring, producing magnetic force that will, that will propel this ring upwards. Now, the amount of current depends on the quantity. We discussed the so-called Ohm's law, where the amount of electrical current depends on the properties of the material. It depends on how materials of different kinds, how well these materials conduct electricity, or rather, how the impurities of this material resist the flow of electrons through these materials. And so some materials are better conductors than others. Electrical conduction of aluminum is not as good as the electric conduction in copper, which is why copper is used in most electrical wires in the transmission lines. So a copper ring can produce a larger electrical current for the same amount of magnetic induction, propelling it higher. And of course, we also discussed the fact that electrical properties of materials change with temperature. Temperature is a measure of vibration in the atoms is a measure of vibration of the atoms in the various materials. And so the more atoms vibrate, the more likely they are to impede the progress of electrons as they flow through this conductive wire. So the resistance of most materials changes with temperature, it decreases with decreasing temperature. You may have heard about devices known as superconductors. These are devices that become completely transparent to electrical currents. They can sustain very large electrical currents and don't impede the progress of electrical currents. And those devices typically operate at low temperatures. At the temperatures of liquid helium, which is about 4 degrees above absolute zero, or some devices now some materials can operate at the temperature of about liquid nitrogen, which is about 70 degrees Kelvin, 77 degrees Kelvin. So to demonstrate that a cold object conducts electricity much better, I will send the electrical current through this loop again, inducing an eddy current. And if you remember in the past, my first try, the copper ring jumped to about this elevation. After cooling, the electrical current increases, producing a much more dramatic, hopefully, effect when my capacitor charges. Like that. So electricity conducts better in materials that are cooled to cryogenic temperatures. Resistance of copper and aluminum is much smaller in cryogenic temperatures, which is, at some temperatures, certain materials even exhibit superconductivity, which is complete lack of resistance to electricity. All right, we talked about oscillations and waves, the fact that we can, any elastic medium can transport energy in the form of mechanical vibrations, like this. These mechanical vibrations are known as waves, and when they propagate through an elastic medium, we discussed the fact that there are two types of waves. The waves that can travel in one particular direction are called, obviously, traveling waves. The waves that are composed of the two sets of waves propagating in two opposite directions, forward and backward, can form a standard standing fixed pattern known as a standing wave. And here are the two examples of the standing wave on the string. So a wave that can fit exactly an integer number of times, whose wavelengths can fit in exactly an integer number of times on a particular string, can form a stable pattern. Here's 1, 2, 3, 4, 5, 6 half wavelengths or 3 wavelengths can fit into the length of the string like this, forming a stable pattern that contains nodes where the vibrations do not happen at all, and places where the amplitude of vibration is large. The standing wave can be characterized by either a wavelength, in this particular case, or a frequency at which the string vibrates. This also leads to applications such as the creation of resonances. Each string like this has a characteristic frequency at which it likes to vibrate with large amplitudes. This is known as a resonance frequency, and leads to effects of enhanced oscillations, for example, vibration of buildings at some specific frequencies that need to be understood when you're designing large objects like bridges and buildings. Or, an effect of the resonance is known to every child when they're swung on the swing, that if you push the swing at very set intervals, at characteristic intervals, you can increase the amplitude of the oscillation without applying a large force with every push. So over time, you can build up the amplitude of vibrations, and this is the effect known as resonance. We discussed sound waves and earthquakes. Earthquakes and sound waves are both examples of mechanical energy propagating through space in this oscillatory wave motion. Sound is an example of compression of air that propagates from the source, like me, to the receiver, like you. We discussed the fact that the frequency that you hear in the sound depends on the speed of sound and the wavelengths of radiation, the wavelengths of this vibration. And the frequency can be changed by changing the speed of sound. The larger the speed of sound for particular wavelengths, the larger the frequency that you will hear in the audible sound wave. And so one way to change the speed of sound is to fill the cavity, vocal cavity that produces the sound, with a gas that has lower or higher sound speed. For example, helium, that's an example of very light gas, has a very large speed of sound that corresponds to a very large speed with which those molecules move at any particular temperature. And so inhaling helium, like this, changes the frequency with which I sound. Sort of like this. So, if I inhale a gas that has high sound speed, the frequency of my voice increases, increasing the pitch, producing low or high frequency, weird sounding sounds. If I inhale the gas that has very low sound speed, heavy gases have low speeds, light gases have high sound speeds. If I inhale the gas with the low speed of sound, my sound will, the pitch of my voice will decrease. And this is the example. This is the, if you hear something like this after 10 o'clock at night, the effect can be dramatic. This is sulfur hexafluoride, a very heavy gas. Sulfur is heavy, has an atomic number of 16, weight of 32. Fluoride is also has an atomic weight of 18, and there are 6 of them. So sulfur hexafluoride is a gas that's about 4 times heavier than air, so the speed of sound in it is about 4 times lower, and the pitch that I produce when my vocal cavity is filled with sulfur hexafluoride is about 4 times lower. Right. And I sound much lower. Okay, so we discussed these effects. We discussed the fact that you can produce, in some cases, you can produce mechanical vibrations that travel faster than the speed of sound in air or in whatever substance you are producing mechanical vibrations, creating sonic booms. An example of a sonic boom is the snap of a whip. The whip is designed in a way that the tip of the whip can travel with the speeds of up to 500 meters a second. That's larger than the speed of sound in air, producing hopefully a sharp crack if I actually manage to do it correctly like this. So, whips are designed to be thick at the base and relatively narrow, thin at the tip, so that the speed of mechanical vibration of the whip increases as the wave, produced by the motion of my hand, propagates from the base to the tip, so that the speed can be as large as a few hundred meters a second, and the tip traveling faster than the speed of sound produces a sharp crack known as a sonic boom. We also talked about the fact that the motion, so this is an example where a motion of the source can produce changes in intensity known as sonic booms. But of course, motion of the sources relative to the receiver can change the apparent pitch with which you hear or see the oscillation. And the example of this is known as the Doppler shift. The fact that the moving objects like this sonalert produce a sound that you hear as pitch at alternating higher and lower frequencies due to the motion of the source relative to you. If the source moves closer to you, it produces higher pitch. If it moves away from you, it produces lower pitch. We discussed light. The fact that light is another example of electromagnetic waves. It's an oscillation of electric and magnetic fields in space and can be produced at different frequencies and wavelengths. The electromagnetic radiation at low frequencies, long wavelengths, is known as microwaves and radio waves. And then visible light is the electromagnetic radiation with the wavelengths of about a micron or smaller, and the wavelengths and the electromagnetic radiation with the wavelengths of below micron and up to nanometers is classified as UV, X-ray, and gamma ray light. We discussed applications of both visible light and ultraviolet and infrared and other electromagnetic radiation. We discussed optics, which can produce interesting effects. Optics is what allows you to focus light, visible light, at, for example, focus them on the back of your retina, producing sharper images. Light can be manipulated with both lenses, like this, or mirrors, producing interesting effects. Here I have a light bulb that can be turned on and off. This actually is a very strange light bulb. I can unscrew it and still have the light on. This is an example of an optical illusion produced by another light source here in a combination of parabolic mirrors. Other optical effects, of course, optical illusion effects are possible. The light perception, the color and the direction can be changed by refraction, by light propagating through curved objects, otherwise known as lenses. And so here's an example of another optical illusion effect. I think I passed it around at some point in class, and you were supposed to tell me why the red word dioxide appears upside down and the blue word glass appears, no, the other way around. Blue glass appears upside down and the red dioxide appears right side up. The reason the word glass appears upside down is because the direction of light rays flips the image, which is what happens in the convex lenses. The reason the dioxide red appears upside down is because this word is symmetric. Actually, if you flip it upside down, it still reads dioxide. This is an example of an optical illusion, kind of a cute trick. Professor Moller was here with you discussing the climate change and the fact that the absorption of radiation varies with the wavelengths. And so, for example, infrared radiation can be trapped by greenhouse gases in the atmosphere, just like it can be trapped by plexiglass in a greenhouse, and the effects that this can have on the environment. And then towards the end, we discussed more modern issues like quantum physics that led to the development of most modern devices, from computer processors, lasers, to solar cells, and even more obscure effects of special and general relativity that have to do with the objects that move very close to the speed of light, or objects that move in the gravitational field of massive planets and stars. And then finally, the fact that we can look at the universe around us and try to understand it from the fundamental principles. So what I try to explain to you over the course of this year is the fact that universe around us is mysterious, but universe around us is still based on fundamental physics laws, and this set of physics laws that I hopefully describe to you over the course of this semester can be used both in applications in your everyday life and also hopefully in order to understand the structure and the mysteries of the universe around us. And that's what we hopefully can take from the studies of fundamental physics. So let me stop here. I would like to, so before you leave, please collect or put the evaluation forms in the envelope, and you collect them. And I wish you good luck for the rest of your studies here in Cal, as well as the good luck 2 weeks from now on the final exam. And I'll see you then. Thank you very much.